The point of this talk really is just to perhaps start some discussions and make you think about what it means to collect data over a large number of people, average it, and then make scientific statements about that. And specifically, how does that interact with us as individuals who have data that means something to us and affects us in our lives? And what is the relationship then between these two things? Because, as I think I hope my anecdotes will show, they're really not the same thing. Okay, so population level statistics, I think it's fair to say, it tells you what to expect for the average patient. I would say that's a succinct way of describing all of this. So, I have a personal example here. My wife, who's called Maya, got chronic tendinitis. Now, if you've ever had tendinitis, you'll know how incredibly painful it is. So it happened in her wrist, and the reason why she had it is because she's the mother of young children. So it turns out that this is incredibly common for mothers of young children. And I think you can imagine why that's the case, right? Because you've got, you're trying to strangle them out. Because precisely for that reason, that they're just jumping around and they want to get their stuff done and they want to do what they want to do and you want them to do what you want them to do, and you've got to carry all the shopping around and you're going to move stuff around. It's quite difficult to organise life with young children. So how will we go about quantifying this problem of tendinitis then? Well, first of all, we would go out and measure some quantity. Let's call it X, say. And let's say X is the amount of pain that's been experienced by the subject. So then we would call P of X is the probability of having that level of pain. So you collect data from very many patients, and now we can know something about the probability P of X. So I've drawn there, that's what X is on the X-axis, on the Y-axis is P of X. So that curve there would be this average level population data that you would get if you collected pain over a large number of people who had tendinitis. So it's some kind of measure. So now what you would do is you go out and apply some kind of treatment. So if you do that, you would expect that the symptoms would change. Hopefully they should. But now, you've got data from people who are treated patients who have been given some kind of treatment, and you can see that their pain supposedly is hopefully less on average. And you've got the distribution of patients that are untreated. And what you can see is you have a treated average and an untreated average. So these two lines pretty much tell you what is the typical patient. What sort of, how often would you encounter them in the population? So now you're a doctor. Imagine yourself as a doctor. Somebody comes to you. See, a young mother comes into your clinic, and you have to make a decision. Do you treat them or not? So let's say you've only got one treatment you can apply. Do you apply it?
Yes.
Right. Okay. Well, you've got all this. You've got now. You go to the literature, and what you see is you've got these two curves like this. So now you've got to ask yourself this question. Given those two curves, what's the optimum decision to make? What's the right decision to make in those circumstances? So this is the basic standard in publication for publication in medical journals. Is a test called some kind of hypothesis test. So you want to look for statistical significance on some hypothesis test, right? So a classical example is so-called the two-sample t-test. So in this test we have two groups. They could be, for example, treated and untreated patients. And the question is, on average, do the groups differ? So, has the treatment had, on average, some kind of effect? That's what you want to know. And so you go out and collect enough data, you can make very fine distinctions in the average. So you can you might find that those two averages are very, very close, but you can say with statistical significance that they are definitely different. So often then, with enough data, significance may be obtainable. But the data, unfortunately, overlap in this example very, very heavily. So a large overlap means that there is no decision boundary that allows a clear separation of the individuals from each group. So measuring the size of the overlap between the two samples gives us the practical importance. Because in this example, there's little practical importance, even if there is a significant difference. So, but practical importance is critical for decision making. Because at the individual level, otherwise, most individuals cannot be reliably placed into one group or the other. So what I put here is a more contrived example where the two cases are very, very well separated. And in which case, there really isn't any ambiguity in making diagnostics or making treatment decisions. Because you know that if somebody is to that side, you'll know that they will definitely benefit from the treatment, and so it's well worth doing it. So then, just quickly back to my wife's chronic tendinitis. Here are the recommended treatments that she was given by the clinician. First one, immobilization. In other words, don't use your arm. So that's totally impractical when you've got to actually get on with life and you've got to do everyday things. The second one, ice pack. Well, she tried that for ages, and that was hopeless. That didn't do anything at all. It just made her arm cold. The third one is painkillers. Now, she has like a real reluctance to take painkillers, and I think most people do have a reluctance to take large amounts of painkillers. And even when she did take dangerously high doses of painkillers, it still didn't seem to make any difference. So, here's another suggestion that was offered. Something more invasive, steroid injections. So, population studies show that it makes a significant difference if you get some kind of I looked at the literature on this, and it turns out that statistical significance meets all the p-values. It has very, very small p-values. If you have an invasive steroid injection, it will make your chronic tendinitis better. So here we can see the graphs that I reconstructed from their data have the untreated baseline in blue and the treated group in black. And you can see that there is certainly an overlap. It's certainly not as bad as the cases that I showed you, the case that I showed you earlier. But there certainly is overlap. It would be possible to imagine that there is a treatment decision boundary in around 4 that you could use to separate these two. But again, there's this overlap. So I mean the p-value is small. I mean it's less than 0.05, the magical 0.05. And by any measure of effect size, it's quite large. This Cohen's d, for example, is 1.3. So should she take that treatment or not? Well, she did. And this is what happened. So that's the decision boundary. And that was Maya's response at about 6. So, after about 12 months, really that treatment hadn't actually worked.
Where did she start?
Where did she start? She was about 8 before the treatment. So yeah, she had got somewhat better.
She recovered.
A little bit, but still not enough to make a difference in her life.
Oh, okay.
You know, you'd want it to go down to 2 to make a difference.
And what is this thing? What does it mean?
It's a subjective reported pain scale. 10 being the worst pain possible. 0 being
the scale is not very scientific as well, because 10 for you is not 10 for me. Yeah.
But it has to be patient
Individual
reported.
heterogeneity.
Yeah,
no,
it's the
I know.
only way,
I mean,
right?
how are you going to,
It's a problem, yeah.
it's a very good, interesting point. How would you actually physically measure pain? Objectively, I don't know. So, at the outset, population data says that she might respond well to treatment. But clearly she deviates from the population average in this respect. So, tendinitis is not that serious, of course, but Parkinson's disease is. Surely you would say that medical science has data that allows unambiguous treatment decisions for something as serious as Parkinson's disease. Yeah.
So I have another question from the previous slide.
Yeah.
So from the previous slide, you can gather
Yeah.
that there's, some sort of average downshift, right? It's not merely
Yes.
like a decision boundary, it's also like how much result. And it looks to me like a downshift of like 2 or 3 is actually consistent with what this suggests. And at that point, I wouldn't find that result surprising, that it wasn't satisfactory. Right, because like, even if you just took the peaks, right, it goes from like a little less than 6 to a little less than 3. So the downshift to around 3.
Well, sure, but it's the absolute pain that matters.
Yeah,
You
yeah.
really
but-
want to get, because,
yeah.
well, I mean, that's what she reports anyway. She said
Mhm.
6 is not good enough. That's not going to make a difference. That's basically agonizing pain, which
Mhm.
means that she can't do anything.
But
And so-
the reason why I say this is because, for instance, if
Yeah.
you start off with the blue curve, it's not like it randomizes the results and then you get the black curve. There's going to be a correlation between what one person said, probably is like an average difference.
So you're saying something like the shift in the peak. You'd want to see the same sort of shift in the peak.
Basically, she has a different subjective measure of success. And so, by this statistical map, your wife's response is predictable. If she's on the extreme tail of the distribution from where your population is. She's at 8. Those people are at 6. She shifted down to 6. She went down 2 instead of 4 or whatever.
Yeah.
But and the distribution is wider of the other people. So some people, on average, are at 2, but maybe there's nobody at 2, right? It's just an average of 8 and 0 or something like that. See what I'm saying?
Yeah, so you have some kind of systematic variation between individuals, and then you have the effect. Yeah, maybe. I don't know what pain is.
I think the suggestion is that you should have plotted the delta rather than the absolute.
I'm sure you have another
Yeah,
question.
anyway, so I mean, that's what the publication said. It had absolute reported pain in there, so I thought, well, let's just see how she compared to the... so the outset, but clearly, okay, so she deviates from the population average, and then tendinitis is not that serious, as I was saying, and surely there are better things that can be done, or better is known for more serious conditions such as Parkinson's disease. But typical information in the literature consists of annual or semi-annual scores, let's say. And it consists essentially of demographic data. And here's an example from a publication talking about a longitudinal study of motor response to levodopa in Parkinson's disease. And pretty much what it says is that you will get worse. So I don't know how really useful that is. Anyway, of course now it's feasible to do personal monitoring, yes? And this is what we're talking about. So we have something like wearable sensors, we have online symptom reporting, there's home-based telemonitoring systems, so we have this opportunity to collect objective and high-frequency individualized symptom data. And survey-based data, online symptom data is now available. For example, patients like me, Paul Wicks gave a talk, who's the research director from Patients Like Me a few weeks ago, and they have self-reported non-motor symptom severity data on their website. More than 5,500 PD patients. 3,500 completed at least one survey, which means that they have about 14,000 or so surveys on this database, which is extraordinary. There are some people in there who are incredible diarists. Some people who have been collecting data for over 7 years, so once every 2 weeks. This is extraordinary by comparison to the current literature that's out there. And the individual level data shows some real surprises. for example, you see dynamic variations in symptom progression rates and responses to treatments. In some cases, there's quite smooth progression, like this person here on the bottom left-hand side. So the x-axis is the years since diagnosis, and the y-axis is the UPDRS score, which for Parkinson's disease just tells you how severe their symptoms are over time. And you can see that this person here is their symptom progression is quite slow. It's fairly smooth, but this person to the right here on the other side has quite erratic symptom variation, which is extraordinary. That tells you something quite different about the way that their symptoms are changing. And this is, again, so we should, talked about the validity of this self-reporting. Well, this is pretty accurate. This sort of self-reporting, because it's a sort of multimodal question set of questions that are asked, and it's no worse than clinical reporting of the same symptoms. So that turns out to be quite accurate data. And
is there a way to know whether the patients themselves record this data, or if there's a
this is all
caregiver?
self-reported.
Okay.
All of it is, yeah.
So not the family member that can be there.
Oh yeah. Yeah. We don't know that.
So there's no way that, the patients like in your website does not ask any question like that.
I don't suppose there's anything to stop. I don't think it does, and I don't think there's anything to stop people from actually entering, from say their spouse entering data for them or something like that.
Has anybody tried to compare the same series of data collected and reported personally versus at the same day or same time collected by?
I don't think so. Not in this data. And so if we compare that to what's in the literature, I think there's a very different story to tell, I think, about individuals' experiences of this disease by comparison to what you get if you average out over a stage of a large number of patients. So I think self-quantification has enormous potential to adjust treatment decisions to individual circumstances. This is what I think is part of the moral to take from that. Okay, so finally back to my wife's wrist tendonitis, an unexpected treatment. It just turns out, through experimentation, she discovered that there are good and bad strollers, for her at least. So it's a happy ending. But not thanks, unfortunately, to population medical statistics. Not thanks. So I think, so the moral of the tale I'm trying to make here is that there are advances in statistical methodology that allow you to quantify the improvement that a specific individual will experience versus the population level data. And I didn't really have time to go into it. It's quite technical. But to say that, I feel that the literature needs to move on, and it needs to start taking into account the kinds of variation that individuals experience. And there needs to be a new sort of way of thinking about this. That's what I think. So thanks very much.
Okay, let's take a few questions.
Are you using like a Bayesian method, like a Gibbs sampling or some kind of a hierarchical Bayes model to model individual?
Actually, in this case, yes, that's what I'm doing.
Okay.
Yes,
I do the same thing with market data and stuff like that.
yeah, exactly. Because you can take into account prior information from the population.
Exactly.
And then you can use that to inform what
To
happens
simulate
in
the
the
distributions
Yeah,
for
and you get a
individuals.
posterior of the
Yeah,
estimate.
that's great.
Yeah. But there are other
But they're not using that now.
No, they're
as
not
you're
using
saying, no.
It's not that common, no, I have to admit.
It's a hassle.
Right.
Yeah,
it's technically more complex, that's right.
And the model run for hours to, right. But
Actually, the technique I'm using here is just really simple Bayesian linear regression, and there are closed forms for it, so you don't have to do computations. It's nice.
okay, so I'll talk to you afterwards.
Sure, yeah. Okay.
So
yeah.
I'm going to throw a little cold water on this.
Sure, yeah.
Who besides the patient benefits from this?
Well, I just feel it is the patient that should benefit from it. I completely understand, like the population level data. Yeah, the population level data matters, of course, to health systems, and of course we all have to share in that. we're all paying into our insurance premiums, and
So the example around this, I'll try to make it really short, is they did the REVEAL study, which was run in Boston, and it gives patients it reveals their ApoE4 status, which is a predictor of early onset Alzheimer's. And the study was to see whether patients got depressed or whether they did appropriate things. It turns out the most actionable thing that they didn't get depressed. What they did is they bought long-term disability insurance. And what happened was the insurance company said, no, you can't do that because it breaks our population statistics information. So again, the way I phrased the question was maybe a little provocative, but it's unclear to me you're going to get traction in the business world around what you're talking about. I think it's great for patients, but you break a bunch of things.
Unless you sell to the insurance company.
Well, but they can't. They can't do that. Well, it's a big story.
I should say,
interesting story.
I should qualify this by saying I don't feel that population statistics is bad. I just think that it has to be augmented with the individual level data, and I think that the two have to meet somewhere. And I think currently there's a disconnect between the way that the research looks at populations, that treats individuals, and that's the only point.
So your one slide proved that perfectly, right? So the one where you have the multimodal distribution.
Yeah.
So forcing a normal curve on that won't work, right? Because there is, sometimes there is nobody in there.
Yes.
There is no average patient. Economists found this out a long time ago, right?
Yeah. It's like, for example, if you break a hip and go into hospital, this can cost, say, $50,000, if not $100,000 a year. Those people who break a hip and end up in hospital are not in the same population as people who don't. So in other words, but they're all treated the same.
Yeah, so there's selectivity bias, right? And someone who's more at risk or whatever will select themselves into an insurance pool or something like that, which changes the actuarial tables and so forth. And that's why everybody has to have health insurance kind of thing to make that idea work.
I just feel it would be better to divide patients up into groups. But anyway, it's
how you measure, right? It's how you measure those distributions, right?
And how you quantify it.
Are there any other questions?
So I guess then, there's an implied decision service, right? You just don't know the data to look for, you don't know which data. The data maybe that the recording isn't necessarily sufficient to make that decision.
Yeah, and bear in mind, of course, that making a prediction for an individual is just one data point. Ideally, you'd want to say, I make a prediction for a patient and this has a distribution. I'm not that certain about my prediction, about whether this patient will be... You need to make probabilistic predictions. You need to say, here's my treatment for you, plus or minus, rather than saying, here's my treatment for you. That's it. That's the treatment. But of course, once you start making those kind of decisions, you have to then qualify how good those decisions have been in the past, and you have to qualify them against the statistical data that's collected. So you need some sophisticated techniques to take into account the mismatch in your predictions against what actually happens. And the current way it's dealt with is it's dealt with just a single decision.
We can wrap up this talk here.
Yeah.
But thank you.
Yeah.